Okay, so 4.5 is the second derivative test. Remember, the first derivative test found max and min using the sign chart. The second derivative test also finds max and min. It does not use a sign chart at all. If you learn and memorize the idea of the second derivative test, it will be faster than the first one. You do need both of them though, so it's not like one is better than the other. We can write questions to where you have to know both, okay? So don't think this is optional or to replace that first derivative test. It's not. So the idea is when you did the first derivative test, you made a sign chart. The second derivative test, since it's using the second derivative, it's based on concavity. So let's say we had a curve that was concave up. Well, if a curve is concave up, you're going to achieve a minimum value. And so what you notice is that if you found a critical point, and that's the key, you're still solving your first derivative and setting that equal to 0. So if your critical point has a second derivative that is positive, that meant your curve was concave up, and so it's telling you that it has a minimum. Okay, I don't need to go from increasing to decreasing or anything else. I don't need a sign chart. We're going to interpret concavity. On the flip side, what if we had a curve that was concave down? So let's say our critical point was right here. Well, the entire curve, especially at that critical point, is concave down. So the sign of the second derivative would be negative, and so you would have a maximum. That's the idea. Now, if your second derivative at the critical point is 0, it doesn't mean you don't have a max or a min, okay? What it does mean is that the second derivative test fails, you can't use it, and so go back to that first derivative test and use your signs. There's a lot of different reasons why this might happen, so I'm not going to go into that. All right, so wait, why do we have to learn this? Well, obviously, time is the first reason. The second derivative test will save you time if you use it, and all you wanted to know was to classify max and min. All right. The second reason, though, which is more important, is that there are going to be problems that they want to see if you know the second derivative test, so they're only going to give you limited information to where the first derivative test wouldn't be applicable. All right. So let's look at example 1. I want to do a trig 1 just for more trig review, but this has a different trig solving review I don't think we've seen this year yet. You did see it back in secondary 3, but I know that's been a long time. All right, so find any local extrema. They don't tell us how to do it. So if I can avoid sign charts, I completely do. It usually means you're doing less trig as well. So I'm going to try the second derivative test. So first I want to find my critical point. Okay, so we're going to take the first derivative and we'll set it equal to 0 and solve. So 1, the derivative of cosine is negative sine, 1d2, plus 2. The derivative of 1 is also cosine. So we end up with negative sine squared plus cosine squared. Now, this is something different. We could solve this because it does want to know if we set this equal to 0, we have two options. I could add sine to the other side and cosine. And so we kind of saw this in the last section. We want to know, where does the sine squared equal the cosine squared? So the trouble though with this is that I could have a positive angle, and because I'm squaring it, it could be positive or negative on both sides, okay? That's option number 1. And you would solve this obviously using your 45-degree reference angle, same as we saw. The second way, this is going to be a new way, I want to introduce in case this ever shows up again. This is actually an identity. If we wrote this as cosine squared minus sine squared, that's a double angle identity from secondary 3. So I'm going to bring that up. I know you don't remember this, but if you see cosine squared minus sine squared equals the cosine of 2 times the angle, okay? There are other double angles. Actually, the sine one shows up a lot in derivative multiple choice simplifying, so that's a good one to know. If you saw 2 sine cosine, you can write sine of 2x. So I see cosine squared minus sine squared, so I'm going to write cosine of 2x, Okay, and we're going to go through this solving since I haven't shown you this before. So I get cosine of 2 times some x value equals 0. So remember, we're solving for x. So on our, oops, I don't even want a sign chart. I want my critical value. Okay, so I need to know if I draw my wave of cosine, and x needs to be on this interval, okay, not the angle. So I'm looking at pi over 2 to negative pi over 2. We'll go back here. Okay. So it looks like, and that's on my interval. So the cosine equals 0 at pi over 2. So I'm going to write this under it because it's going to make sense in a second. And also I know that the cosine of negative pi over 2. I'll write it over here. Cosine of negative pi over 2 equals 0. Okay, and so let's just do the first one. So because I know that this is true, I'm going to isolate it here. These are acting in the same place. So in order to find what x is, I can set up an equation. So we can say 2x has to equal pi over 2. And because these angles are what equals 0, I'm just trying to find out what value of x do I need in order for that to be pi over 2. So if you divide by 2, we already have a bar down here, so it goes in the denominator. So x equals pi over 4. And that is between pi over 2 and negative pi over 2. We're going to do the same thing because I know that the cosine of 2x equals 0. So I want this to solve for x. Well, all that's going to do is make that. So we actually have 2 critical values. We have pi over 4 is critical, and we have negative pi over 4 is critical. And those are possible points of inflection. Okay? I know that might take you a little bit to absorb. Now, what we want to do though is we want to do the derivative because we want to use the second derivative test. Okay, stay with me. So I should have made this a lot bigger of a box actually. So I'm going to go down here. No, I'm not. I need more space. All right. Well, what we know is that my first derivative is the double angle, okay? And I want to use this one because it's a lot easier than doing that derivative because that's a lot of chain rules. So there is a reason why remembering double angles will be helpful. So the derivative of cosine is negative sine. The inside stays the same, and then we'll multiply by the derivative of the inside, so we get a 2. Now what we want to do is we want to take these values and plug them into the second derivative just to see their concavity. So let's get some space open. I know I'm erasing half my work, but I need some space. So f double prime of pi over 4, which is 45 degrees, is equal to negative 2 times the sine of 2 times pi over 4, which is pi over 2. Well, the sine of pi over 2, think about your wave, is 1. So this is going to be negative 2, which means my curve is concave down, which means there's going to be a max. Okay? And then I want to try negative pi over 4. I'll do it down here. I was going to cheat, but I won't. So I still get negative 2, and then I get sine of negative pi over 2. So the sine of negative pi over 2, remember your wave. So pi over 2 is 1, negative pi over 2 is negative 1. So negative 1 times negative 2 is positive. So now I know my curve is concave up, and so that means we have a min. Okay? At these x values. Okay, I know it's tricky because I use that double angle. I wanted to show that solving strategy because this is new. We haven't seen it before. Do you have to know that? I don't know, it could come up. It makes your derivative easier. There could be times where you do. So it's just good to review. All right, let's go to my second example. All right, so on this one, it says if my first derivative when x equals 2 equals 0. So what that means is we have a critical value at x equals 2, because my first derivative equals 0. And my second derivative when x equals 2 is negative. So second derivative is negative, which means concave down. Determine whether f of x has any local extrema. Well, it might have more extrema, but based on what we know, 2 was critical, so that's important. And my second derivative was concave down, so we have a max. So I would say yes, x equals 2 is a local max by the second derivative test. It doesn't ask me to justify, but I wrote that it's critical, and we wrote that it's concave down. Okay? All right, let's look at number 3. It says, find the critical points for f of x, determine whether each is a local max or local min. And I just picked a different function. So critical values mean my first derivative set equal to 0. So let's find it. So I get 1, and then I'm going to rewrite this as 4x to the negative 1. So power rule, so minus 4x to the negative 2. I'm going to set that equal to 0, and then I'll write it nicer. Okay? So to solve this, I'm going to add to the other side. Because it's equal to 1, I can multiply by the denominator as long as x does not equal 0, because that makes this undefined. So I get 4 equals x squared, take the square root, and x equals plus or minus 2. So what I want to do is we want to find our second derivative. Now, typically, 0 wasn't defined for the original. 0 is not defined for the first derivative, and 0 won't be defined for the second derivative. So 0 is not in the domain, okay? So it can't be a max or a min. So my second derivative is going to be another power rule. So I get positive 8 x to the negative 3, which is 8 over x cubed. So I know f double prime of 2, let's say. Well, 8 over 2 cubed is positive, so we get concave up, so we know that that is a minimum. F double prime of negative 2 would be 8 over negative 2 cubed is negative 8, so we get a negative number, which means concave down, and so that's a local max. 0 is not in the domain at all, so I don't need to test it. It's not in the domain, okay? F of 0 does not exist. All right, we're not going to spend a lot of time on this. This could be a question on a free response that just asks you about using concavity to determine if a value is an underestimate or an overestimate, if the tangent line lies above or below. So this would go in hand of writing equation tangent lines and our tangent line approximation, linear approximation. And I'll just kind of talk about the idea. So a question like this, it was a free response question, I think from 2014. And it just said, let f be this function defined by x is greater than 0, so it's a domain restriction, telling us a specific value, and give us the first derivative graph, okay, and the equation. So on part A, it said, use the graph of f prime to determine whether the graph of the original f is concave up, concave down, or neither from 1.7 to 1.9. And so since they gave us the derivative, we want to know, well, where's 1.7 to 1.9? I know it's somewhere. Oops, I keep doing this. It's somewhere around here. but it's hard to pinpoint that exactly. Well, what we notice though is that if this is the graph of f prime, f double prime refers to the tangent slopes to f prime. Okay, does that make sense? So what we know, let's do purple, is that if I want the tangent slopes, it doesn't even matter if I knew exactly, but all of these tangent slopes, what do you notice? Well, they're all negative. So I know that the second derivative from 1.7 to 1.9, or even from probably like 1.3 to 2.1, they're all negative. Okay, so that means since our second derivative is negative, that means that we are concave down on the original. Concavity refers to the original graph, okay? Does that make sense? So that's what I would say. F double prime is less than 0 for all x from 1.7 to x to 1.9. Since since the tangent slopes to f prime of x is negative. Okay? All right. Part B, it says on the interval from 0 to 3, what x value does the graph of f have a relative maximum? So remember, a relative max meant that our first derivative equals 0, and that the first derivative goes, remember if we have a max, we go from increasing to decreasing, goes from positive to negative, and that's by the first derivative test. So let's see. So we went from 0 to 3. Well, that's kind of what's shown. We just want to know, where does my derivative, which is what's shown, go from positive values to negative values, and I'm looking for where it equals 0. So my possible points are the red dots. So let's go ahead and erase. Okay. So these are possible max and min. So here my derivative's positive, my derivative's negative, my derivative's positive. So we wanted to go from positive to negative. So that is going to be a local max. And that's what they want to know. So that, if we wanted to set this equal to 0, well, e to no power equals 0. So I'm looking for, where does sine of x squared equals 0. So remember, the sine of x is equal to 0 at pi. So that means that x squared equals pi. This is kind of the same reasoning I used on that double angle, okay? So we know that the sine of pi equals 0. And we know that the sine of x squared equals 0, because that's what we're solving for. So that means that these have to be set equal to each other. So that's why I know x squared equals pi. So if I take the square root, I'm looking for plus and minus, but we don't have any negatives on the restriction. So I know that that is at root pi. So that would be my justification. The sine, I'll write it down here. So sine of pi equals 0. Sine of x squared equals 0. Therefore, x squared equals pi, x equals 0. So at x equals, why did I write that? I don't know why I wrote 0. Root pi plus minus. So at x equals root pi, all of this justification. Okay. I had the rules, I had the value, All right, and part C says write an equation of a tangent line. So I'm looking for y minus y1 equals my slope, x minus x1 at x equals 2. So I've got 2 and I'm going to need the y value. So we're going to plug in 2 into the original. Oh, they tell me right there. 5.623. Oh, that's awesome. So 5.623. And so now I need my slope when x equals 2. So when x equals 2, I don't have it, but I can plug that in. So if I plug in 2, I'm going to write e to the negative x over 4. And what was that? Sine of x squared. So if I plug in 2, f prime of 2 equals e to the x over 4. So 2, so e to the negative 1/2. And then sine of, this would be radians. So 2 squared, so sine of 4. And like I said, that would be radians. That's my slope. So I get y minus y equals m x minus x. And remember, you don't have to clean up this tangent line. Now they want to know, will the tangent line be above or below the graph from 1.5 to 2? So remember, we're going to use concavity. So from 1.5 to 2, we know this is the derivative. So we know the second derivative, since the tangent lines are negative, the second derivative is going to be negative, okay? So the second derivative is negative, concave down, for x from 1.5 because the tangent slopes to, don't say of, the tangent slopes to f prime are negative. And so what we know is since it's concave down, think about when you have a curve that's concave down, your tangent lines are above the graph. So we're going to say above by second derivative test. Okay? So you really want to connect the idea of concavity and then realizing that tangent lines are above there. But in order to find the concavity, you have to remember it's the derivative of f prime, which is given, so we want the tangent slope values. Okay? Yeah, that was it. All right, let me know if you have any questions. I know it's a lot of ideas. I tried to pick the more difficult ones to give you a better review. Okay? All right. Good luck.